a a vase or a vase is radially symmetrical. So it counts as a solid of revolution. Well, a sphere is a solid of revolution too. Like it's got many axes of symmetry, but any shape like that counts as a solid of revolution. So that's the thing that has to be special about it. It gets more complicated finding the volumes of things that are not so symmetrical. Can anyone think of any other solids of revolution? Just sort of that you might see. Yeah, a cylinder. A cone. This water bottle, largely, aside from the threading, which can't be radially symmetrical because then it wouldn't work. This canister of Play-Doh that has been here since the first day for some reason, that's a solid of revolution. But what we're going to do today is we're going to find the volumes of these kinds of shapes. And on Thursday we'll learn another method, but today we will take each of these shapes and decompose them into disks. And later, washers, which are just disks with holes in them. And so what that's going to look like is just sort of imagine that you have like a deli slicer. And I kind of forget what a deli slicer looks like, but I don't. Those are teeth. And like. Okay, whatever. But just imagine taking a cone and just putting it through that deli slicer and just shaving it into a bunch of, circles. So that the cuts would happen like, sort of like this. Should have chosen a color other than red. Okay. So like that. Now, obviously, there are more circles than this, but and what you're going to do is, in a very mathematical way, you're not going to sort of do this by hand, but in some sort of mathematical sense, you are taking all these individual circles and adding them up together to find the volume. As opposed to, using some volume formula or something. And the idea is that there are, if you do this in real life, there's going to be a finite number of little circles, of thin little circles. But the idea is that, you're doing this mathematically. So there are infinitely many of these circles, of these disks, and they are each infinitely thin. Very sort of similar thinking to the how you might break down an area into a bunch of little rectangles. So that's where the integration comes in, because you're adding up an infinite number of infinitely thin little things. And really, the only difference is going to be you're going to have to account for the fact that these are circles or disks in shape. So we're going to find the volume of a solid of revolution using the disk method, right, which is sort of what I just described. The washer method is the same as the disk method, except the disks have a hole in the middle, so call them washers instead. And we're just not going to do the last one. It doesn't matter. I mean, you can see it, but, it's not that important. It's just that you can extend this decomposing into circles. You can extend that to shapes that have square cross-sections or triangular cross-sections instead of just circular cross-sections. You can sort of extend this method however much you like. Okay. So a solid of revolution is some sort of area that is rotated around an axis. So imagine there's a rectangle lying right against an axis of revolution. Like this. Now, of course, that's a two-dimensional area. But if you were to imagine that you could sort of pop this out into 3D for a second, and sort of sweep this out around the axis of revolution, so that it sort of left a shadow or a trace of itself the whole way through, like you just sort of it just forms. It would just form this sort of thin cylinder, this thin flat disk, as it rotated around the axis of revolution. And so it has a radius of r. The disk would have a radius of r. That's the height of the rectangle. And the disk would have a width of w, right? However wide the rectangle was to begin with, that's how wide the disk is going to be. But it's going to have a radius of r, however high it was to begin with. Now, the volume of this disk is going to be if I remember correctly, pi r squared h. So, in general, the volume of a cylinder is pi r squared h. Yeah. Pi r squared h. Except in this case, our radius is like a big R, like whatever big R is here. And h, it's actually sort of on its side, so the h is actually w. So the volume is pi big R squared w. And that's the formula that's sort of going to inform the method that we use. Okay, so if a rectangle has a given width and a given height, the disk that is made by sweeping it out around an axis of revolution is going to be that same width. And it's going to have a radius of whatever the original height was. Okay. Right, nothing really new there. Now, so this involves taking a rectangle, rotating around until it forms a disk. Now, if you have a bunch of rectangles, and you rotated that bunch of rectangles out to form a bunch of disks, it might look something like this. So imagine that there is a curve that sort of looks like this, some sort of function of x. This is one of many possible representative rectangles that you could use to sort of approximate the area underneath, right? Because that's what integration ultimately is, even though you sort of learn this basis for integration very early on and then kind of don't revisit it in favor of like formulas and stuff. But ultimately, it is just taking a bunch of rectangles underneath an area in order to approximate the area. So right now I've got, 6 rectangles. I'm going to rotate them out to be like 6 cylinders, and that's going to give me an approximation of the volume of the true shape, the shape, the 3-dimensional shape that's in blue right here. These 6 disks are going to give me an approximation of that, in the same way that a bunch of rectangles give me an approximation of an area underneath the curve. And the idea is that, after 6 disks, you might get a better approximation by doing 10 disks, or 15, or 50. Not that you're actually going to have to calculate 50, the volume of 50 different disks. Well, that's the basis for this approximation. So through integration, we're going to sort of see what happens when we get this to be infinitely many disks. And so if you notice nothing else, at least notice that the width of any individual cylinder is given by delta x. When we increase the number of cylinders to infinity, so that they're infinitely thin, because there are infinitely many of these little cylinders, that delta x is going to be better described by dx, an infinitesimal change in x, as opposed to, delta x, which is still sort of a real number. Okay, so before we established that the volume of any of these disks is given by pi big R squared W. Now, if you think about the change in volume, all the radiuses are still the same, but as you increase the number of cylinders, the width is going to become thinner. The width of each rectangle is going to become thinner and thinner, and it's going to be better described as delta x. And I'm sort of skipping a lot of math that's probably not all that relevant to you here, but and this is going to be a really sloppy statement, but if you integrate both sides of this, r squared is the same. Yeah. As you take this to infinitely many rectangles, the delta V changes to a dV. And the delta x changes to a dx. And the integral of 1 dv, or the integral of dv, is just v. So really, what you're going to be able to do is to get the volume by integrating pi times the integral of r squared. Now, r is the height of each rectangle. It's basically the height of the function at any given point. So r is just going to be, whatever expression the function uses, and you'll sort of see what I mean later. But this is going to be the formula. That is sort of the fundamental basis of this disk method. So it just follows from the volume of a cylinder. Pi r squared times the width of each. And the width is the dx. And the radius is the function value. Right. They're, yeah. So this is, on Thursday we talked about the idea of a representative element and how it can contribute to, integration formulas in a process that's sort of the same every time. You take a formula from before calculus, like the volume of a disk. You sort of figure out what the representative element is, and then you just integrate both sides to sort of signify adding up a bunch of those representative elements, and then you have your formula. Pi r squared dx. Pi times the integral of r squared dx. Okay, so here is sort of what it all comes down to. These are I guess they're formulas, kind of. but I mean hardly. It's just the formula for the volume of a cylinder with an extra integration symbol. Okay, but if you've got a horizontal axis of revolution, so just sort of like the example that we saw, this is the formula for that. Pi times the integral from a to b of r of x. R of x represents the radius of the disk, and it's a function of x. And that gets squared. And then, integrated. And that's if you have a horizontal axis of revolution. Now, if you have a vertical axis of revolution, so for example, you're taking some shape and you're rotating it around the y-axis, so that there's a vertical axis of revolution. You're going to have this formula instead. You're going to be writing your radius as a function of y. So the only difference between these two is that one is in terms of x and the other one's in terms of y. And that's all got to do with the shapes that you're making. So if you're using the disk method for, as this is what this is about, and you're rotating it around a horizontal axis of revolution, you can sort of imagine that the, you're taking the shape and sort of slicing it up into a bunch of tiny little slices, like this, and then rotating these slices around to form thin little disks. And if you draw in these little, little slice marks, you can sort of tell that your integral should be dx. Because these thin little vertical slices, they have a width of dx. And they're infinitesimally thin with respect to x. So that's if you have a horizontal axis of revolution and you're forming these disks. If you have a vertical axis of revolution and you're forming disks, well then your slices must be going, in order for you to form disks, your slices must be going horizontally. And the, infinitesimal thickness of each of these slices is best described as dy instead of dx. Imagine these lines are straighter. And there's going to be a mnemonic that will not make sense to you right now, but will make sense to you later once we learn the other method of finding these sorts of volumes on Thursday. You can write it down at this point or not. But that mnemonic is going to be really only the first part of it works as a mnemonic because disk and perpendicular do not rhyme. But shell and parallel rhyme, so once you know what the shell method is, then you can sort of reason, okay, well, if shell the shell method is based around, the slices being parallel to the axis of rotation, then the opposite must be true for the disk. And so you'll notice that in each of these cases, whether it's dx or dy, it is the disk method because these slices are perpendicular to the axis of rotation. That's going to be important, or that's going to be the easiest way to tell what method you're using. So we'll see an example here. Let's click on the last. No, wait, hold on. Crap. Actually, I guess there's no real need to. Okay. Alright, so there is this sort of weird semi-ellipse. Not exactly, but this weird quasi-semi-ellipse shape. And you want to rotate it out so that it forms this kind of weird football shape. If you take that silhouette and you were to rotate it around the x-axis, you would end up with this sort of three-dimensional football. Now, a couple of things to note. The bounds of integration are from 0 to pi. Also, we're using the disk method. So our slices should go perpendicular to the axis of rotation, the axis of rotation being this horizontal x-axis right here. So our slices should be vertical, and you can sort of see that with the representative rectangle there. And since these, little slices are going this way, is this integral going to be dx or dy if we use the disk method? Yeah, right. These are, all these slices are, infinitesimally thin with respect to x. So the integral is going to be in terms of x. You want your function in terms of x, which it thankfully already is. The function that describes the radius is right here. The square root of sine of x. And it describes the radius of each of these disks because it's the height, the height of each rectangle becomes the radius of each little disk. So that's kind of all the information you really need, I believe. Now at this point you can figure the volume is pi times the integral from a to b, so from a being 0, and I'm just going to say x equals 0 to be clear, and b is x equals pi. So the integral from a to b of whatever function describes the radius, which in our case is the function square root of sine of x. It's that squared. Dx. That's it. That's the whole integral that's going to give us, the volume. a and b are 0 and pi. The radius is given by the function that describes that curve. Okay. So, simplifying that a bit, that's pi times the integral from 0 to pi of, well, the square root of sine of x. If you square that, that's going to make the square root go away, so you're just going to get sine x. You know, you won't always be so lucky, but in this case, they cancel right out. Now, the integral of sine is negative cosine. Right, and if you integrate, you don't write the integration symbol anymore. You write an evaluation bar. So the integral of sine of x just is negative cosine of x. And you're going to evaluate that, you know, remembering that the pi is in front, you're going to evaluate that from 0 to pi. So that's pi times negative, and you can factor out the negative sign if you want, but pi times negative cosine of pi. That's what's going to come first. Minus the same, except you're going to plug in 0. So minus pi times negative cosine of 0. Now the cosine of the angle pi, you know, cosine is the x value of whatever, you know, point you're at. So at the angle pi, that's over here. That cosine is negative 1. But we have the negative of that, so this is going to be positive 1. So pi times positive 1. Or just pi. Now the cosine of 0, angle 0 is over here. It's the positive x-axis. It's where you start at. The cosine of that is positive 1. The negative of that will be negative 1 times pi. But then you're subtracting that, so it's positive 1 times pi. So this is just pi plus pi. Or 2 pi. So that's the volume of this solid of revolution. It is 2 pi cubic units in volume. Which is to say, you know, it occupies somewhere around 6.28 cubic units. Now, I wanted to talk about what happens if you're not just rotating something around the x-axis or the y-axis. There might be situations in which, let me just check this first. Yeah, okay. there may be situations, and I almost never actually get to this in the class. There are situations in which, so an example of that would be, you might be taking an area like this, and of course, at this point, you might expect, oh well, you can totally rotate around the y-axis. Forms a neat little cylinder shape. But there may be other situations, and we'll talk about this after we talk about the washer method, where maybe your axis of rotation is all the way over here instead. And so if you rotate it around that axis, the shape that it's going to make is, here's the sort of original cross-section of this shape. The shape that it's going to make is this sort of weird cylinder donut thing. So that is definitely a possibility, and I'll tell you guys how you can sort of account for that later on. That really looks terrible. Yeah, it's probably better. Okay, but this is going to require some small modification to things we're going to learn. Alright, so what if instead of being right up against the axis of revolution, or the axis of rotation, your shape, the silhouette that you're sort of taking and sweeping out, is actually, what if it wasn't right up against it? What if it was sort of just away from it by a little bit? In that case, you do not have discs, but you have washers. And the way that you describe washers is with the use of a big R for an outer radius, and a little r for an inner radius representing the whole. Now, very much like finding the area between two curves, the only difference that's going to make is you're going to take the big radius squared and subtract the little radius squared. You're just taking the outside, subtracting the inside, same as when you are finding the area between two curves. You're basically sort of finding the volume in between two radiuses. You don't actually have to write all this down, by the way. I mean, all it is it's just going to come down to a formula with an extra little r squared in it, and otherwise it's going to be the same as the disk method. Because it basically is just, if your solid of revolution has a hole in it, it's kind of like you're taking one solid of revolution and subtracting out another smaller solid of revolution out the middle. So All right. So the washer method is going to have to be used whenever you have any shape that is not right up against the axis. If there's any space between your shape and the axis of revolution, you're going to need to use the washer method. You're going to need to consider it as there being an outer radius and an inner radius. So if you took this sort of lens-looking thing and rotated it around this horizontal axis of revolution, what you would end up with is this sort of weird, I don't know, kind of megaphone-looking thing with a curved inside. And, as you do more of these, you'll get better at sort of conceiving what three-dimensional shape a two-dimensional region is going to make once it's, rotated out. Okay, but you can literally think of this as a solid cone minus a weird sort of little inside region. So this is there's a pie in here, but this is what it would be if it were just the big radius, the outer sort of edge. And this is what it is if it's just the inner radius. So you're taking this sort of solid, shape formed by the outer radius and subtracting away from the interior the shape that the inner radius forms. So that's why it's going to be big R squared minus little r squared. And so that formula is right here. The only difference between the disk method that you just learned is the addition of this minus little r squared. And it really just is like you're using the disk method twice. Once for the outside and you're subtracting away, doing it from the inside. Yeah. And otherwise everything else is the same. There's still the pi in the front. Still goes from A to B. Still dx. And the version of that's dy. So this is for a horizontal axis of revolution. I mean, not like you really need both. Like, they're not two separate formulas. They're the same. But if you have a vertical axis of revolution, they're just going to be in terms of y, and the integral is going to be dy. That's going to be pi times the integral from c to d. I mean, it's not really different from a to b, but it's just like c to d is usually used for the balance for a dy integration. Times the radius as a function of y squared minus the big radius as a function of y squared minus the little radius as a function of y squared. Yeah, so that's dy. Oops. That's just if you wanted a different formula for dy explicitly, but so we'll attempt to apply this sort of at this time. So there's this weird lentil-looking, this tilted lentil-looking region, And you're going to rotate it around a horizontal axis of rotation, meaning that the integral is going to be dx, because this is discs. Discs have slices perpendicular to the axis of rotation. And so it's going to form this sort of... I mean, the outer edge is going to be sort of a bowl, but the interior is going to be this sort of weird convex cone-shaped hole. Not that that's super important, you know, it's not like it's not like knowing what the resulting shape is going to really help all that much. But so we establish this integral is dx. So the bounds should be in terms of x, and the bounds that are x values. They appear to be 0, x equals 0, and x equals 1. If you were not absolutely sure that that was the case, you could find out, you could find out where these intersect. So if, these weren't marked as 0, 0, and 1, 1, you could find out your points of intersection by taking one curve, taking the other curve, and setting them equal to each other. You can square both sides to get rid of that square root. You could move everything to one side. You could factor out an x. And so you could solve for, you could probably figure it out from here that x is 0 from here, and that from this, x is 1. Okay. But the integral then is going to go from 0 to 1. That's going to be, x equals 0 to x equals 1. Those are for sure your bounds of integration. Don't forget the pi in front, because I always do. And then it's just going to be your outer radius squared minus your inner radius squared. Now your outer radius is whichever one is further away from your axis of revolution. Now your axis of revolution is the x-axis right here. The the edge, or the function that's further away, and thus forms the outer radius, is this y equals square root of x. That's sort of up here. This is big R. And this y equals x squared, that's little r. So big R is the square root of x. And that's going to get squared. And then you're going to subtract little r squared. And the integral is going to be dx. Because you're perpendicular to your axis of rotation, your slices are sort of going this way. And then at this point you can just simplify. It's just all going to be power rule once you simplify it. So that's pi times the integral from 0 to 1. If you take the square root of x and you square it, well, that's x. If you take x squared and you square it, that's x to the 4th. So we got x minus x to the 4th for the integral of that. Now the integral of x is x squared over 2. The integral of x to the 4th is going to be x to the 5th over 5. That's just the power rule. And that's going to get evaluated from, right, because we have integrated, so there's no integral bar anymore. is an evaluation for it. It's going to get evaluated from x equals 0 to x equals 1. Okay, so if I plug in 1, it looks like what I'm going to get is 1/2 minus 1/5. If I plug in 0, this is a polynomial integral. If I plug in 0, I'm definitely going to get 0. So minus pi times 0. Just to remember that you get, just to be able to tell yourself that you didn't forget to do it. It just turned out to be 0 when you plug in 0. But 1/2 minus 1/5, that's the same as 5/10 minus 2/5. No, 5/10 minus 2/10. 5/10 minus 2/10. So 3/10. 3/10 pi. That is the volume in cubic units of this shape. Right, so the actual integration is not really very difficult at all. Like, there's no secret techniques or tricks or anything like that. But it's just setting up the integral in the first place that tends to be pretty difficult. Or like not difficult. I mean, I'm not going to tell you it's difficult, because then you'll believe me, and then you'll tell yourself that it's difficult. Yeah, it's easy. It's a breeze. Don't worry about it. Let's check it out. Yeah. Okay, so we'll take a break right now. Return at 9:20. All examples we've been doing, right, they've all been dx integrals. The slices have all been sort of vertical. The axis of rotation has been horizontal, and so they've all been dx integrals. Now we're going to look at an example of what happens if the axis of integration, or the axis of revolution, is vertical instead, and you kind of actually know that. That's going to result in a dy integral. But let's see how that's going to affect this particular shape. Okay, so the top of this region is described by y equals x squared plus 1. Now that's a problem for us, because we're wanting to do this integral dy. Because we're rotating around a vertical axis of rotation, and so our slices have to be dy slices, meaning that all our functions that we're going to use have to be in terms of y. But you can actually just take this function y equals x squared plus 1, solve for y. So y minus 1 is going to be x squared. And so the square root of y minus 1, the square root of all of y minus 1, that's going to be x. And that's the way in which you're going to want to describe this curve, because you want it to be in terms of x. Your integral is going to be dx. You want to describe your functions in terms of x. Now, if you take a second, then you draw and you draw out the slices that you're going to be making, these sort of horizontal dy slices. What it looks like from 0 to 1, relatively straightforward, right? This sort of forms a rectangle shape, and so when you spin it out around that vertical axis of rotation, it's going to form a cylinder. You know, the inner radius is just x equals 0, and the outer radius is just x equals 1. So, for this portion, and I'm pretty much just saying the same thing that this is, the radius as a function of y, that's the equation x equals 1. So just 1, really. You can say r of y equals 1. And little r of y equals 0. And that's for this portion. Really, it's x equals 1. X equals 0. Just like when you have a function of x, usually you describe it as y equals. If you have a function of y, you can describe it as x equals. And if you sort of take this portion separately, I know there's a lot here. Let me move this stuff over here. Here, the big radius, the radius that's farther out away from the axis of rotation, that's still 1. That is still, you know, x equals 1. And the inner radius is going to be the square root of y minus 1. It's the same curve as y equals x squared plus 1, but it's described in terms of y now. So this is actually going to require 2 separate integrals. And we're actually going to revisit this on Thursday because with the other method that we're going to learn, this is actually much easier. And there's no need to split up into 2 integrals when we're using the other method that we're going to learn. Okay. So, washer method. 2 separate instances of it, actually. And it's going to be dy. It's kind of a lot to squish together into one problem. Okay. Let's just deal with this bottom part first. Okay, so this little piece. And then over here, we'll deal with the other part. Okay. So here's the lower part, and the volume of that is going to be pi times the integral. We're doing this dy, so our bounds of integration are going to be y values. Y equals 0 to y equals 1. And so that's going to be the big radius squared. Now the big radius is just 1 minus the little radius squared. And the little radius squared is just 0 because that little radius is just x equals 0. I mean, you don't even have to put it, honestly, because, yeah, it's right up against the axis of rotation, so you can actually just say, yeah, you can just say it's a disk. Or it's like a washer with, like a non-existent hole in the middle or something, yeah. Yeah, so, integral of 1 squared is 1. The integral of 1 is x. So this is just, no. Ah, crap. It's dy. Okay, the integral of 1 with respect to y is y. So you got pi y that you're going to evaluate from 0 to 1. Well, definitely if you plug in 1, that's pi. If you plug in 0, that's nothing. So this is just pi minus nothing, or pi. So the area or the volume that you get from rotating out the sort of square-shaped lower part, that's just pi cubic units. Now this other part, that's going to be the integral pi times the integral from your bounds of integration are going to, again, be in terms of y. They're going to be y values. And so the y value that starts at is 1. So y equals 1. And it goes all the way up to y equals 2. And this one, because you're rotating it, this way, it is going to be a washer, this one, this part. Because it's not right up against the axis there. So the outer radius is 1. This vertical line x equals 1, that's the outer radius. So you can just say 1 squared. So 1 gets squared minus the inner radius squared. Now the inner radius is this curve described in terms of y as the square root of y minus 1. So we're going to take the square root of y minus 1, and we're going to square it and subtract it away. And that's the integral. It's dy. There we go. Simplifying that a little bit. I'm just going to continue writing y equals for the bounds of integration, just so I don't forget. But 1 squared is 1, and the square root of something squared is just going to be the thing underneath. So it's 1 minus all of y minus 1. Don't forget those parentheses, because these aren't going to cancel out. It's going to be y minus 1. 1 minus y plus 1. Or, if you simplify it a little more, just 2 minus y. dy from y equals 1 to y equals 2, with the pi in front. And the integral of 2 is going to be 2y. The integral of y is going to be y squared over 2. There's a pi in front, don't forget that, and it's going to be evaluated from y equals 1 to y equals 2. If you plug in 2, that's going to be, what, 4 minus 2? Right? 4, 2 times 2 is 4. 2 squared over 2 is going to be 2. So that's just, if you plug in 2, you get 2 pi. If you plug in 1, you get, what, 2 minus a half, so 3 halves pi. Two minus 3 halves, 2 is equivalent to 4 halves. 4 halves minus 3 halves is 1 half. So pi over 2 is going to be the volume of this region. Pi is the volume of this lower region. Add them up together. The volume of the, sorry, not region, volume, or like regions don't have volumes, volumes have volumes. This whole shape is going to have a total volume of pi plus pi over 2, or 3 pi over 2. And on Thursday we'll learn a better way to deal with something like this, something that requires us not to have to break up and volume into two separate volumes, and do a different integral for each. All right. Sure. Okay. Yeah, I mean, this lower region. You're literally taking a square and spinning it out. So you could have used the geometric formula, pi r squared h, to find that volume. Not like this was super difficult, anyways, but you could have. Yeah. I mean, you can do stuff like that. That's no real problem. Yeah. Okay. And we're not actually going to talk about this, but just know that what it would be about is, we've looked at circular cross sections or disc-shaped cross sections, but you could theoretically do the same with like square cross sections just by using a different formula. Instead of using a pi and an r squared, for square cross sections you would simply use like whatever the side length is squared. It would be a little more involved for a triangle, but you would find a way to express the sort of area of each triangle, and use that in your formula. You don't actually have to know this stuff. All right, so first I am going to, expertly draw these lines, or these curves. Well, if you factor in x, that's going to be 4 minus x, so 0 and 4. Okay. Okay. Now, y equals x squared is, that's just a parabola. I'm just going to draw that in sort of here. It's not, this isn't going to be super accurate or nothing. But that's, that's sort of what it would be. In this other parabola, this is a parabola, you can factor this to make it a little bit easier. You can say, okay, well, y equals, if I factor an x out of there, that's 4 minus x. So that means it has x-intercepts at x equals 0 and at x equals 4. So it has x-intercepts right here and here. And it's a downward-facing parabola. Its axis of symmetry is going to be here. You can just, you can also just try to graph this using a graphing calculator. But so it's, so this downward-facing parabola is 0 here and here, right in the middle at x equals 2. Pretend to plug in 2. That's 8 minus 4. Okay, so that's 4. So it occupies the point 2 comma 4. It sort of has a shape like this. Okay, but the enclosed region is this. This sort of, again, lenticular sort of looking region. Let me just label these real quick. This is y equals 4x minus x squared. And this parabola here is y equals x squared. Don't worry about there being a second one yet. Okay. So in this first case, the x-axis. So let's say we're taking this region and rotating it around the x-axis. And so the shape that that's going to form is, again, this sort of weird, well, I can't even describe it. It's like a bowl, but it's kind of weird, sort of. It's like a weird bowl with like a wormhole inside. Okay, but that's the shape that that's going to make. Okay. Now this is a washer, right? Because there is some space in between the region and the axis of rotation, so you got to take your outer radius, square it, subtract your inner radius, square it. So that's pi times the integral. Oh, and because the axis of revolution is horizontal, these slices are vertical. And so this gets to be a dx integral. Very nice for us. Don't have to rewrite anything in terms of y. So, with respect to the axis of integration, the outer radius is very clearly this green. It's the one that's further away from the axis of revolution. It's the green parabola, or it's the green curve. So that's your outer radius. So that is 4x minus x squared squared. That's your outer radius squared. Minus your inner radius squared. Your inner radius is clearly this blue parabola here. So that's x squared, and that gets squared. Dx. Now as for the bounds of integration, you can probably tell that the x values where they intersect are 0, and maybe you can tell that that's 2. But again, if you couldn't tell visually, you could just set the two equations equal to each other. We got x squared equal to 4x minus x squared. Add x squared to both sides. Actually, no. Subtract x squared from both sides. So you get 0 equals 4x minus 2x squared. Then factor out a 2x. Oops, 0 equals, my mistake. Factor out a 2x, and you're going to get 2x minus x. No. 2 minus x. Okay. Okay, that's going to give you x equals 0 as one point of intersection and x equals 2 as the other. So those are your bounds of integration. Not too terrible. Okay, now we've got to expand these. 4x minus x squared is not going to be, this is not what it's going to be. It is not going to be 16x squared minus x to the fourth. You don't just square both things and then call it a day. That is a binomial, so if you have a squared binomial, that represents 4x minus x squared times 4x minus x squared. And so it's not just going to be the first thing squared and the last thing squared. There's going to be these whole other things to it. That's going to be 16x squared minus 4x cubed minus another 4x cubed plus x to the fourth. And then the x squared that gets squared, that's just minus x to the fourth. That's not really. So just don't make that mistake if you have to take a binomial and square it. Don't just square the first term and square the second term and then say that that's it. I think this x to the fourth is going to cancel out with this x to the fourth. So really, all you're going to have in the end is there's a pi in front. Pi times the integral from 0 to 2 of 16x squared minus 8x cubed. Once you combine those, dx. Really not very much. Okay, that's going to be, once you integrate that, that's going to be 16x cubed over 3 minus 8x to the fourth over 4, so 2x to the fourth. Evaluated from 0 to 2. If you plug in 2, you're going to get what? 8 times 16 is 128 over 3. Minus, that's going to be 32. Okay. Minus, well, pi times 0 minus 0. Okay. 32 is 96 thirds. 128 thirds minus 96 thirds. 32 thirds. Okay. So 32 thirds pi is going to be that volume of that region. Let me just check that real quick. Yeah, okay. Okay, so that's the sort of straightforward, the more straightforward of the two, the one where the axis of rotation is just the x-axis. Now, what if the axis of rotation were not the x-axis, but instead the line y equals 9? That is to say, what if instead of rotating around the x-axis, we actually rotated around 5, 6, 7, 8, 9. What if we actually rotated around here? And we actually took this and just sort of like all the way up here and all the way back down. And it would sort of result in this other shape. Kind of similar in some ways, but also not. there's just this giant hole in the middle. Like this weird onion ring kind of thing. What would the volume of that be? Well, with the disk method, all you need is a few adjustments. And there will actually be like a whole video explaining like in better detail like how this stuff gets dealt with. But I just wanted to talk about it in class because I never get to. Okay. So just a reminder that that axis of rotation is now y equals 9. Here, and let me, or just erase this real quick. Okay. So what that means is that little r is no longer just this 4x minus x squared. Little r is actually, right, so okay, 9 minus 4x minus x squared. I mean, and honestly, you could do 4x minus x squared minus 9. Because you're squaring these, it's not going to matter which, like, if you take 2 minus 1 and you square it, that's 1, If you switch the order and you do 1 minus 2, yeah, that's negative 1, but once you square it, it's 1 again. So it doesn't actually matter which order you subtract these in. You can do the curve minus your axis or the axis minus your curve. It doesn't really matter. But the outer radius, the big R, is 9 minus this blue curve, x squared. That's the difference that it's going to make if your axis of rotation is something different. You're going to do your axis minus the curve. Whether you're talking about an inside radius or an outside radius, you gotta add in the radius minus the curve. So this is how that's going to look different. It's going to be pi times the integral, still from 0 to 2. But a couple things are different. For now, for example, the outer radius is actually this blue curve now, or it involves this blue curve now, because your axis of rotation is up there now. And so the one that's further away, forming the outer radius, is this blue curve. And so that's 9 minus x squared. So that's the outer radius squared. I guess I should do that in black. Okay. Minus the inner radius is 9 minus 4x, in parentheses 4x minus x squared. And that gets squared. That is a trinomial. Hopefully that's not as horrible as it seems. Okay. So just sort of simplifying this a bit, you could write 9 minus x squared times 9 minus x squared and then FOIL it out. But all it's going to be is the first thing squared, 81, minus 2 of the cross product, so minus 9x, 2 of those, so minus 18x squared. Minus 18x squared, plus the last thing squared, because that's going to come from the negative x squared times negative x squared, so plus x to the fourth. Okay. Now that's the first thing. And I'm just gonna do this. 9 minus 4x plus x squared. Okay. I guess that's not horrible. Are there two numbers that multiply to 9 that... No. Okay, maybe that is going to be kind of bad. Okay, well, I guess I'll just, square this trinomial. Yes, that is not nice. But it's 9 minus 4x plus x squared times itself. So it's going to be a lot of things. But I'll just, Okay, so that's... okay, 81. So 2 of these. I guess, yeah, minus 36x plus 9x squared. Okay. And then distribute the minus 4x, so that's minus 36x again, plus 16x squared, and then minus 4x cubed. And then distribute the x squared, that's plus 9x squared minus 4x cubed, plus x to the fourth. And that is all inside of a set of parentheses that's being subtracted. This sucks, but okay. I'm just gonna skip a couple of steps here. Minus 81, 36, 36, minus 72, so plus 72x. The x squareds, there's 9, 25, 34. So minus 34x squared. For x cubed, there's minus and minus, so plus 8x cubed and minus x to the fourth. Okay. Yuck. I guess you could combine some of those things together. But anyways, this is the inside of the integral. So that's the integral from 0 to 2 with the pi of, if you combine these, negative 18 minus 34, 52, yeah, negative 52 x squared plus 72x plus 8x cubed dx. And then you would just use the power rule on all three of those terms and plug in 2 and 1. Once it becomes 10, you guys can leave. I'll see this through to the end. So negative 52 cubed over 3, it's 52. 52 is not divisible by 3. Okay. So negative 52x cubed over 3 plus 72x squared over 2, so 36x squared. And 8x to the fourth over 4, so 2x to the fourth. Okay, that gets evaluated. There's a pi in front, but that gets evaluated. From 0 to 2. Okay. Negative 52 times 8 is negative 416 over 3. Plug in 2. 4 times 36 is 144. 2 to the 4th is 16 times 2 is 32. And when you plug in 0, there's, in this case, there is nothing. Okay. So this will be 176, which in terms of thirds is 528 thirds. Okay, so it's negative 416 thirds plus 528 thirds, the difference of which would be 112 thirds. Okay, so pi times 112 over 3. Which is thankfully correct. Okay.